the nice thing is that I'm not going to ask you to differentiate between lambda and delta isomers. They're hard to do. But I'm going to give you some examples of compounds that do have both delta and lambda isomers. So let's talk a little bit about how chelating agents bond to transition metal atoms. I want you to notice that a chelating agent, or a bidentate ligand in this case, like ethylene diamine, can only bond in cis positions. So the two nitrogens, if the A's represented nitrogens, can only bond cis to one another in this compound. Notice that you can have it so that the two chelating agents look just like this, where they're not trans to one another, they're actually cis, or you could have where they're trans to one another. Remember that the bidentate ligands generally only span cis positions. They can't reach around the compound to span trans positions. So for example, if we look at trans-diaqua bisoxalato chromate 3, you'll notice that this compound has the oxalate ion bonded. Of course, the oxygens are in cis positions, but the two oxalate ions are 180 degrees apart from one another. That means it's trans. That's why we say that the waters are trans, and that also forces the oxalate ions to be trans. It should be noted, actually, before I move on, that this is not optically active. So if you drew its mirror image, it would look exactly the same as what I'm showing right there. Now in this case, and I'm going to show you a shortcut for how you can draw out an oxalate ion or ethylene diamine. You many times can just use a curved line between the two chelating atoms. Now I may ask you to draw out the structure, the Lewis structure for something like oxalate, but if you want to show it in the bonding of a coordination compound, you can just use the curved line like I'm showing here in my figure. So in this case, the two water molecules are now cis to one another, forcing the oxalate ions to also be cis to one another. If you drew its mirror image, you would notice that its mirror image does not superimpose on this molecule. Therefore, they're enantiomers. So there's a pair of compounds, an R and an S, that have this exact same formula, just different configurations of the chelating agents. So now, that's enough on isomerism. I'm going to let you guys read the rest, or read up on it and learn more in your textbook. I plan on posting a file on Moodle to show you how to draw isomers, or all the isomers of a compound systematically. Let's now do a survey of coordination number for the rest of this lecture. Coordination number, remember, is the number of ligands or chelating agents that surround a metal atom or ion in a coordination compound. Now, most coordination compounds have coordination numbers in geometries that are very well known. Most coordination compounds are either octahedral, that's the most common, they have a coordination number of 6, square planar and have a coordination number of 4, or are tetrahedral and have a coordination number of 4. However, other coordination numbers do exist. They're just rare. Here are the factors that influence coordination number. First, the number of bonds that form between a metal cation and the different ligands leads to greater stability. And as a matter of fact, we'll talk about an effect where chelating agents have a tendency to stabilize coordination compounds very well. you'll find that Vesper works very well for simple main group metal coordination compounds. However, when you're looking at transition metals, the bonding interactions are between ligand molecular orbitals and the transition metal d orbitals. The steric effects, this is an effect we'll talk about a little later. When you have bulkier ligands and chelating agents that surround a metal atom or ion, there'll be less of those that can pack around it because it's just too big. Finally, there's a crystallization effect. If a compound will form a solid effectively and has a certain coordination number, that will influence how many ligands coordinate around that metal cation. So let's start out with the simplest coordination number, which is coordination number 1. It doesn't exist very much, and as a matter of fact, I had to kind of dig around to find a good example. Normally you find coordination number 1 where one atom on a bulky ligand bonds to a metal cation in the gas phase, but there are some examples out there. For example, if you look right here, that is an indium atom, and you've got this huge bulky ligand with lots of carbons bonded to that indium atom right there. So it does exist, it's just very rare. Coordination number 2 is also rare, but you do see them. You generally get a linear arrangement of the ligands around the metal cation. Coordination number 2 is observed in metal cations that, or in copper 2+ and copper+, silver+, gold+, and mercury 2+. The best known example of a compound or ion with a coordination number equal to 2 is diamine silver 1. So that's shown right here. Here's the silver 1+ cation, and it forms a coordinate covalent bond with each amine ligand, and it's almost perfectly linear. Other complexes that you can find with this coordination number equal to 2 include mercury 2+, gold+, and copper+. Notice that all these metal atoms are D10 cations, and sometimes you can find these linear arrangements of ligands when you have an early transition metal with a bulky bidentate ligand. Now, coordination number 3 is rare as well. Once again, this continues to follow what you know through Vesper. That's why I had you review it at the beginning of the semester. There's going to be a trigonal planar arrangement of the ligands. Now, this coordination number also forms with transition metal cations with a D10 electron configuration. And medium bulk ligands like triphenylphosphine. So keep that in mind, because I could ask you what is the most likely coordination number if I combine copper 1+ solution with triphenylphosphine, and you should know that just because it's got a medium bulk and that it's one of these D10 metal cations, that it should have a coordination number of 3. Now, all of the 4th period transition metals except Mn3+ will form a trigonal planar coordination will form trigonal planar coordination compounds.